get on a fundamental domain, and which we call MAE. From a fundamental domain. So today, I will focus on infinite translation surfaces, but of very special kind that are similar to the one in the Winfrey model, that are covers. So, and actually they will be regular, but I will call them normal to not overlap with the talk we had about regular tailing. So normal covers of compact translation surfaces. And the Winfrey model is an example of such surfaces. So tomorrow it will be about the diffusion. So this is the filter which is in the theorem that Samuel presents. The fourth talk will be about recurrence and transience. And the last one on Friday about reversibility, which is a bit more technical. So that's all. Then, yeah, let's start with. Compact. Oh, I don't know if compact is a well terminology. So finite genus. Compact translation surface. So if you remember the Winfrey model, you have this surface MAE. And the question is, how do we pass from this MAB to the Winfrey model? So we lose some information, but the information we lose is somewhat captured in some data on the surface. And so each copy corresponds to a reflected copy. And yes, perhaps you want the gluings. So this is glued to there. This is glued there. And you repeat the pattern. This corresponds to the obstacles, which is here. And so you pass in a reflected copy, but this side is glued to this side.
Can you write a little bigger, please?
Bigger?
A little bigger.
From now on, yes.
From now on.
And so, this side is particular, because if you cross it, you change from one fundamental domain to another one. So this is exactly the information you need to go from this surface to the Winfrey model. Is to care about the horizontal pieces that I'm writing here, and the vertical transition between the fundamental domains. And so each time you cross one of these curves, you will change from one fundamental domain to the other. So this corresponds to the original copy. So let's say that we go up when we cross this in the positive with the positive crossing. But this is a reflected copy with respect. You are there when you pass through a horizontal. You made an horizontal rebound to get there. So if you cross the same curve, you get down. So here, each time you cross in the positive direction, you should do minus 0,1. In the same way, each time you cross here, it's also a plus, but here it's a minus. And for this, it corresponds to the horizontal direction, but it's quite similar. Those two correspond to going on the right, and those two, which are the reflected copy, correspond to go on the left. So now imagine I have Z2 copy of those. So what I will do is to build the unfolding construction of the Winfrey model that Samuel just drafted. So let's call it, I don't know, until the AB, which is the cover of this, with fiber Z2. And how is it built? You pick Z2 copy of this, and you glue them according to what is written on there. So this is normally glued to this, but in M tilde AB, you glue this side to the copy at +1. So this is the union of MAB times Z2. So this is not exactly MAB because you need to cut, so we cut along check and check. It is bigger or not yet. And what you do for the gluings, you glue back the red and the blue, but with respect to the numbers which are written. So this is an example of normal covers of compact translation surfaces that I want to generalize. So pick the translation surface, so compact. By compact I mean finite genus and singularity of finite angle. Compact translation surface. And as you know, the covers of this, let's call it M, the covers of this surface are parameterized by the fundamental group of M. But here, we want to allow branching over the singularities. So, branched covers of M are parameterized. So parameterized, I mean topological, up to topological equivalence are parameterized by the fundamental group of M minus the singularity of the surface, or the set of branching points. So perhaps here you saw it, perhaps not, but this is unbranched. Okay, and so concretely, what do you do? And I want to consider very special kind. I want to consider only normal covers. Are the one for which the deck group acts transitively on the fibers. The deck group acts transitively on the fiber. So it is not very interesting to say it that way. So concretely, you just pick a normal subgroup of the pi1. So this is concrete version of what I just said. So you have your surface M, and you imagine that it is done with only one polygon. Let's say it that way. So this is A, this is A, B, C, C, D, D. And yes, just this is a big group. If sigma is not empty, this is a free group. So if sigma is different to be empty, it is a free group. So just to mention that you have a lot and a lot of covers. So if you have a surface and if you have a group, you have natural generators for your pi1. If your surface is represented by a polygon, you have natural generators. So you pick a point for a base for your fundamental group, and you choose the curve which goes from one side to the other. We call it theta b. Yes, curve is over here. There is the theta a, theta c. So these are closed curves on my surface, and there is a d which goes from here to here. And it is easy to notice that theta a, theta b, theta c, theta d is actually a basis. I mean a basis of the free group of phi 1 and sigma, where sigma is a set of singularity. So here I only have one singularity. It is all these points are the same. And I get a free group on 4 generators. So now, given my normal subgroup, n in phi 1, what should I consider is the quotient of I should quotient on the left. I quotient on the left because I want to multiply on the right. But most of the time, everything will be abelian, so I don't care about the quotient. And so we consider this quotient, and let's call it f. F as fiber. And what you do, you cut m along these, along the boundary which is written here, and you pick f copy of your surface m. So m tilde associated with this subgroup is just the initial surface cut along the side ABCD times the fiber. And how do you glue everything back together? Now you have nice generators. So the generators, you can push them in F. So it has a. So you can consider the map which goes from the fundamental group of F, which is the projection. And so, moreover, you have multiplication by these elements on the fiber on the right. And this is how you glue back the surface. So imagine that I have C, A, B, C, D, A, approximately. And imagine here, this is a copy small g. Where do I glue everything? I glue this side, so this is copy G. I glue this side, so G in F. I glue this side to the copy G times theta A, which also belongs to A. And the theta A which is below, I glue this A to this one, but in another copy. And I do the same along B, C, D. And that way, I get exactly the cover with this normal, determined by this normal subgroup. So, yeah, this is general construction of normal covers. And why is it normal? This is because the group has transitivity. And why is that so? Is that because L is normal, this quotient is actually a group. And so this group gives you a automorphism of that surface. And so each copy looks the same. This is sort of homogeneity of that cover. So now I want to turn to dynamics. So Samuel introduced interval exchanges. For normal covers. So if you pick exactly the boundary here as a transverse section, so I'm always interested in the vertical flow. So if you pick this interval, which belongs to the surface, as Samuel mentioned, this segment belongs to here. So if you look at the first return time of the vertical flow in that segment, it's exactly an interval exchange transformation, here with 4 intervals. So G, CAB, CBA. And so this is on N, but on N tilde, if you pick all intervals which belong to all copies that you get, what you get is called a skew product. So let's call the interval I and the map T. So T. So I call it S. S is not good, sorry. So, but I never used it, so it's okay. I want to call it TF, which is a map which goes from I times big F, which is my fiber, to I times big F. And so this is infinity. You have one interval in each copy. And what is a map? It's actually easy to describe. If you have a point x, g, you send it to x, g of f of a eta. Let's say eta x, where eta x equal eta a if x belongs to the interval associated with a. So if x was here, you see that I pick my point x here, and I look at the first return time on here, I change from one copy to the copy which is determined by multiplication by eta a. So the copy in which I get is the multiplication on the right by eta a. So if I am in A, I want to multiply on the right by exactly eta a, sorry. So this is just right multiplication. And yeah, if you are in B, you want to multiply by eta B, etc. So this is what we call a skew product. And so this kind of map is called a skew. So there is an F here and there's an eta here. I'm sorry. So generally, I want to write it that way. You have a map xg, which maps to x and g of something which depends on x.
Do you also want a G in this?
What?
Do you want a T in this?
Definitely yes. Thank you. If there is no T, it's not really the first return time of the flow. So yes, I want this map to be the first return time of the flow on the infinite surface. So I need a T here. And what is important here is to notice that if I take powers of this map, is what I'm interested in, is long time behavior of the translation flow. So I want to iterate this map. And if you do that, it's just, in the first component, you just act like T. So it's just T and X. But in the other component, something interesting happens. You are multiplying along, you are multiplying by the value of F along the orbit of X. So this is in the general case, but if the cover is abelian, so what does it mean? Abelian means that the quotient, so F is a group. This F is a group because it's the quotient by a normal subgroup. If F abelian means F abelian. This means if it's abelian, it means that everything here commutes, and I can even write it with plus instead of multiplication. And so these terms become G plus F of X plus F of Tx, blah blah blah. And this quantity is what we call a Birkhoff sum. And so, Birkhoff sums of a function on interval exchange is actually completely related to understanding the flow in some infinite surface. So here, you have 16 intervals. So you can do exactly the same construction. You start from the 16 intervals that operates Samuel writes explicitly the interval exchange, and on the copy which corresponds to this part and this part, you just have a function for which the values are written on the blackboard. So the function f, so let's call it I, the union of these four intervals, and you have a function from I to z2, and the values are here, so I just write f restricted to a00. A00 is that guy, d00 is this one, after that is c and d. So f to 00 is plus 01, f to d00 equals f restricted to c00 equals 0, and f restricted to d00 is plus 10, and then you end up. So this is a particular construction of that. So that's all. Now I want to do some algebraic theory of skew products. So this will be a bit abstract, but the theorem I want to emphasize are some links between. So what are the quantities we want to discuss? So I erase everything, but it is recurrence, transience, and diffusion. So recurrence and transience and diffusion. I won't speak about ergodicity. I will let it for the last course. So diffusion rate. So I want to introduce some quantities, but in this general scheme, and then I will discuss some relation between them and some relation between properties of the group F that we use to make you cover and properties that you expect to get. So perhaps it's good to make a reminder of what happens for random walk on groups. So it will be very quick. So you can think of it as a random walk on a group, except that the steps you are doing are not completely random, but determined by the orbit of your point x. So if you do a random walk on a group, what we know is if your group, so about recurrence and transience, so recurrence, it's actually equivalent to have, so when you have a group, you have a kilograph. You can consider kilograph. In kilograph, you can measure the size of balls, and this is equivalent for growth of balls in G. So my group is F. Sorry, F is less than quadratic. And for the diffusion rate, so the diffusion rate is the exponent at, perhaps I should define it, but before defining it, I will say something. If F is abelian, let's say some ZD, then in each component of ZD you can apply the central limit theorem and you get a diffusion rate of 1/2. Independently on the dimension. So yes, this is a big parenthesis. So interval exchanges are a bit too particular, so let's consider a map T from x to x, and if you don't want to consider a general map, just think of it as an interval exchange. So a map between Borel space.
Sorry, Vincent.
So an interval is Borel. Yes?
Sorry, probably I didn't get it. Then the balls there for the word map?
Oh yeah, there is there is something wrong here. Sorry, there is mean 0, and your question was what about that?
Whatever what's the metric then?
The metric on the kilograph.
Okay, what?
The growth of balls does not depend on the metric on the kilograph. I will speak more about growth of balls later. Spaces that preserve a non-atomic measure mu. So an interval exchange is a perfect example of that. So think of it as an interval exchange. And the measure mu is a Lebesgue measure. Because your interval exchange is piecewise translation, you preserve the Lebesgue. And so given a group F, and given F from X to F, we can build the skew product, as I did before, from X times F to X times F, given by Xg is mapped to Xg times M of X. And what I want to do is to study general properties of this Tf.
Tx.
Correct?
Tx.
T? No, this is a F. Now it is a F, sorry.
Very last thing you wrote.
What?
You left the T out.
Oh, yes. Thank you. Yeah, you continue to remind me that there is a T. So, yeah, first of all, perhaps this is one of the best theorems in periodic theory. This is about recurrence. This is Poincaré recurrence theorem. Lelièvre. Or I don't know. So, non-atomic, sorry, here there is a probability measure. I want this measure on x to x to be finite. My interval is finite, so the Lebesgue measure on it is finite. And I can scale it to be a probability measure. And what I did not mention, so F will be a discrete group, sorry. And on this discrete group, I have a counting measure on F. So everything is about measures. Counting measures on F and mu times lambda, mu times lambda, which lives in x times F, is invariant under my skew product F. So exercise. So what does it mean invariant? I write preserved here, but what does it mean? It means that for any A, so all my sets are measurable. So I want that the inverse measure of a guy is a measure of itself. Yeah. This means preserving the measure. And you can check that the product of the initial measure with the counting measure on the fiber is actually preserved under this skew product. And this is because here the counting measure is a hard measure for the group, and when you act by unification, you preserve that measure. So this is why it is inverted. So here you pick, so the same scheme as here, mu proba preserved. Then we have recurrence. So what does it mean, recurrence, in that scheme? For any A with positive measure, there exists some time after which Tn of x, no, for almost every x that belongs to A, there exists a time at which you go back to A. So this is for finite measure, but as you see, if you start from an interval exchange and you pick F a finite group, this measure is finite, and this theorem applies as well. So it applies in any context when the measure is finite. So the proof is really easy, so I want to do it. So to prove it, it's the same as proving that I prove that for any V included in A, there exists n positive, so with positive measure. There exists n positive such that the measure of T minus n of V intersected with B is positive. So, and this is clearly equivalent to what we wrote here. And how do you do that? You have something of positive measure, which is B, or A as you wish. And when you iterate it backward, so mu of A is the same as mu of t minus 1 of A is the same as blah 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 as mu t minus n of A. So all these sets have the same measures. And your total mass is finite, so you need there needs to be an intersection at some point. So and the total mass is finite. So this implies that there exists two index, n1 and 2, positive and different, so that t minus n1 of A intersected with, so my A is B, sorry. But if you prove the statement for A, this is the same as proving it for B. The measure of that is positive. But once you do that, you just, so imagine that n1 is bigger. So you rewrite it as t minus n2 of t minus n1 minus n2 A intersected with B. Intersected with B. And because this preserves, so this is equal. And because this preserves the measure, this is also the measure of this. Then for times n minus n2, you are going, you go back to the. So in finite, if you preserve a finite measure, you automatically have recurrence. So where it is non-trivial here is because my fiber f is infinite and I have an infinite measure, and recurrence is no more automatic. So an example of a map for which you do not have recurrence. So example, you pick x dot x plus 1 from R to R. So this preserves the type measure, and clearly you do not have any recurrence. So no recurrence. So the question is, for infinite case, do we are in that situation, or can we still have some recurrence? So what is precisely what do we mean by recurrence? So precise definition. When should I stop? 55. Okay. Definition. So TF. So TF is my skew product here. Is recurrent if for A in the base with positive measure with respect to the measure in the base, there exists n positive such that mu. So you look at the time for which you come back arbitrarily close, but also for which you come back arbitrarily close in the fiber. So as my group is discrete, I want it to be in the identity. So I introduce a notation here. So this is the identity on F. Is of positive measure. So what is this Fn of x? This is just the product along the orbit which determines the nth power. So this is just to say that you come back to the same fiber and you come back near your initial set. So this is just the very same recurrence as somewhere introduced. And so I won't do the proof, but there is an equivalent definition for recurrence. No, there are two equivalent definitions, but when the map T is invertible, so I will only state it at the proposition. This is not hard to prove, so you can try to do the proof. So pick TF, and as before with the measure mu and all that, and assume that T is invertible. So I mean invertible as a Borel automorphism. So for the double exchange, T minus 1 exists, so it's invertible. Then are equivalent almost every x in x G. No, there exists n, sorry, there exists n positive such that. So this is the same as going back to the fiber, but not necessarily linear. This is equivalent to saying that TF is recurrent. And this is also equivalent to saying that TF is what we call conservative. And what is conservative is mean wandering sets are of zero measure, and so I should define wandering sets. So there is one, this implication does not need invertibility, but when you go from here to from 1 to 3, you need invertibility. So this sense, no invertibility needed. So what is wandering set? Wandering set is just useful when you use it in proofs. For the definition, it's not that interesting, but when you do a proof or something, and I will use it if we have time, I hope I will. So wandering set is to be included in your space, which is x times f, such that t minus n of b are disjoint. So you have a set, and when you iterate it in the dynamics, everything is disjoint. So in the map x plus 1, if you pick the interval 0, 1, this is a wandering set because it does not intersect. Okay, so now I want to turn to diffusion rate, and I want to make some relation between the diffusion rate and the recurrence. So if it is not recurrent, we say that it is transient. And so perhaps before, there is an assumption which will come a lot of time, and we saw it in the talk of Rodrigo. It's about ergodicity and unique ergodicity. So if you have your map which preserves the probability measure mu, it is ergodic, called ergodic, if A including x t minus n 1 of A equals A implies that the measure is 0 or 1. So it's sort of irreducibility of the space. You cannot cut it into two parts, such that both are invariant in dotted dynamics and of positive measure. So this looks like indecomposability. So when you turn to an infinite measure, you have to take care about what definition you should take for ergodicity. And for internal exchange, there is something wonderful. So this is Kerckhoff-Mazur's-Magny theorem. So if M is a translation surface, so for almost every theta, so you fix an angle and you look at the translation flow in that direction, the associated translation flow is uniquely ergodic. And you can even take the interval exchange, which is the same, the associated interval exchange is uniquely ergodic. So this is stronger than being ergodic. So what is the difference between uniquely ergodic and ergodic? So I guess that Rodrigo defined a unique ergodicity, which is unique invariant measure. And when you do have ergodicity, you have one important theorem, which is Birkhoff theorem, which is one of the so if t from x to x preserving mu a proba probability measure is ergodic with respect to mu, then so I want to consider the growth in the fiber. This is related to what to the diffusion rate. For if you pick a map x from x to r, so this is only abelian case, but there is no general theorem for non-abelian case except for Soledad's theorem. Then for f, L1, so integrable with respect to mu, for almost every x. If you look at the Birkhoff sum of your points and you average over n, as n tends to infinity, this will look like the integral of f. So this means that x the orbit of x equidistributes with respect to the measure here. And in case of unique ergodicity, you can replace almost every by every. So unique ergodicity can replace almost every by every.
But f has to be continuous.
What?
F has to be continuous.
Right.
You also want x to be compact.
Yes. I don't want to enter in detail right now because I want to state a theorem about skew products. So if you do not know that, don't be scared. They will appear in the next talk. This is just to mention that if you start with a function f, which has a positive measure with respect to a positive mean with respect to mu, you cannot expect that your construction will be recurrent. So imagine that this is z and no more r, and you look at the growth of these sums, and so if this is positive, the sum will look like n times the integral of f d mu. So you have no chance that this will be recurrent. And actually, there is a nice theorem which says that the converse holds. So if t from x to x preserving mu ergodic, and t, you assume that it is invertible. You pick f from x to z. Then we have equivalence. So this is the theorem of Atkinson. Which go back to, if I'm not mistaken, 76. Then are equivalent. So you consider the skew product. Tf is recurrent. And 2, the integral of f du equals 0. So there is one direction which is easy, which is this one. And the other one is not. But it's not that hard, and you can even look at the paper of Atkinson, which is, the proof is 1 page long, so it's manageable. I plan to do it, but I have no time. What I want to do is to introduce diffusion rate and to state a theorem about a link between the diffusion rate and the recurrence. So, take the general scheme. So you have a map X from a group F now, and those two theorems are dedicated only to the abelian case. So the next one is, you can manage to make it work when the dimension of the group, this theorem actually should work when you replace Z by something of dimension 1, which is not really interesting, it is virtually Z because of Gromov theorem. Diffusion rate, so what is it? Theta. This is a growth, the Limsuk, the very same way Samuel introduced it. You look at the farthest distance you get up to time n, because now this is discrete time. So the distance, so this is a distance in the kilograph. So you pick 1 kilograph of f. So there is a log. The distance of identity of G f n of x over log n. There is a log. Yes. And so this exists almost every x. So if, sorry, we need ergodicity. If t from x to x is ergodic, theta exists almost every x and is constant. And so I have time to write. And so this is this is 2/3 we get in the Winfrey model, and there is an interesting relationship between the diffusion rate and the dimension of the group. So what is perhaps dimension is not that good. This is not what people call dimension group. So
Sorry. I'm a little bit confused about the diffusion rate. What's the relation between T and F here?
T. Oh yeah, there is T from x to x. And you look at the function which allows you to build the skew product from x times f to x times f. And fn is just the product f of x times f of tx times blah blah blah.
Okay.
The position in the fiber.
Okay.
So you look at the farthest distance in the fiber you get up to time n. And you take the lim sup. And so this can not be greater than, so this is smaller than 1. Because it do not go faster than speed 1. So to do this, if the map, the image is finite, it's no bigger than 1. And so at the very beginning, I make a reminder about random walks, and there is something special which happens with respect to the dimension. And here as well, but you have to take care about the diffusion rate. And so I will call the dimension of f. This is the logarithmic growth. So this is not a very good definition, I am sorry. Logarithmic growth of all in f. So in the Kelly graph of f. So what is important is that the dimension of zd is d. So it is nice to call it a dimension. And actually, there is a Gromov theorem which asserts that if your dimension, as I defined, is finite, then it is integer, and your group is actually virtually nilpotent. So, Gromov. Dim f finite implies dim f belongs to n, and f is virtually nilpotent. So your group is not ugly. You cannot have crazy group in order to consider the dimension. So my theorem only applies to those virtually nilpotent groups. So this is the theorem. And you can find, so that's not my theorem. It is not written like this in the literature, but you can manage it. So you pick, as before, t from x to x, ergodic, and this is important. You pick your function f from x to f, and let's say with finite image. It's just in order to make, if f is completely crazy and you can go very far in one step, then this may be larger than 1. You need some integrability condition on f. So in order to not state it, I just write it like that. Then if the diffusion rate, so theta is the theta of Tf, is smaller, strictly smaller than 1 over the dimension of the group, then Tf is greater. Oh, we're in ergodicity. Sorry. I think I do not. Ah yes, I need ergodicity in order that theta is well defined. So if theta, then Tf is recurrent. And yes, I have 1 minute to make the proof. This is perfect. So just before making the proof, just a comment. In the Wien tree, theta is 2/3, and dimension of f is dimension of Z2 is 2. And so, even if you prove that, yeah, 2/3 is not smaller than 1/2, this is easy, lemma. Then, if even you prove that the diffusion rate is 2/3, you do not get automatically the recurrence. So this might be useful if you have a very small diffusion rate, you automatically have recurrence, which is nice. So proof. I won't do the whole proof, but the way it goes. So if it is not recurrent, so people wonder what we do. We pick a wandering set. Set A, and we can always assume that it is contained in the fiber that is at the identity. So wandering set, I recall, is a set for which when you iterate it, sorry, there is one thing which is important here, invertible. When you iterate it, the copies are disjoint. So what you do, you consider A, T of A, T square of A, blah, 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 and these are disjoint. And because I assume invertibility of my transformation, all of these are the same measure. So up 2 times n, this will fills n times the A in measure. But because you have this equality here, but the distance from, so here you have to care about quantificator, but for many x that belongs to A, the distance from the distance from the identity in the fiber to Fn of x is actually smaller than n to the power theta. You fix an epsilon, and this is smaller than n theta plus epsilon. And so you have 2 quantities, and you can find out that you cannot belong to a ball. So this means that all these sets belongs to this, imply that this belongs to some ball of radius n to the theta plus epsilon. And then, what is the growth of the ball? This is given the dimension of f, and so you put dimension of f in power to get the number of elements, and you get a contradiction with the growth here. So sorry, it's a proof, it goes back and forth between. But this is it.
So we're supposed to use the Atkinson model at some point?
No, nowhere. Here, there is no need of Atkinson. Atkinson is Atkinson is very interesting because you need that theta is lesser than 1, but for many functions it is actually equal to 1. That stuff. So in Atkinson, it is Atkinson is stronger than this result. But these are disjuncts. Yeah. Atkinson and this theorem are 2 theorems which may be useful to use in transition. Yes, and just to finish, if you want to read something, there is a nice paper of Pat Cooper and Barack Weiss in the context of translation surface and mostly on abelian covers. And then there is a book of Schmidt, but I think that you do not want to read it. And that's all.
Questions?
I had a question about Atkinson again. It seems that Atkinson works when the map goes from x to the integer.
To zero, yes.
But then it seems like the group you're working with for the wind tree is
Z2. Yes, it does not apply to the wind tree, but it applies to the infinite band, for example. Yes, I did not mention the band. If you pick a billiard in the infinite band and you put some regularly displayed obstacles, okay, then this is recurrence by Atkinson.
But then Atkinson is not true for, say, parameter
For
group of parameter.
Z2, you mean?
Yeah.
No, because I will prove that there are cases where your basis is uniquely ergodic, but you are divergent, you are transient. So Atkinson does not, you have 0 mean, but it is divergent, transient. But what you obtain in Z2 is actually you come back infinitely often on the horizontal axis and on the vertical axis. And even on any line. You draw any line, and any trajectory will cross infinitely often the line. And this is true for any line. So this is what Atkinson tells you, but it does not tell you that you come back to your initial point. If you project around, yes. Projection recurs, but not necessarily the best.
I actually had a second question. And when you have your deck transformation group acting, it acts for compacting, right?
Yes, because you get X. Yes.
X.
Yeah, okay. You get exactly the compact surface you start with.
Okay.
So what can you say when you don't have versatility? Because sometimes it's useful.
Sometimes it's useful for internal exchange. It is not useful because it's original. I'm pretty sure that this theorem works in invertibility case, but then you have to iterate backward and you have to take care about what you are doing. But Atkinson, actually I don't know. In the proof it is often useful to have invertibility because we can manage. But in that case I don't know. I think I can answer it later. I don't want to say something wrong.
Other questions? Okay, now we'll reconvene at 10:30.